In this video, we will discuss about nucleophilic substitution reactions of the carbonyl group. What are carbonyl compounds? Carbonyl compounds are compounds that contain a carbon-oxygen double bond. And this part is common for all the carbonyl compounds. And the part that is different is here. We call them as Y. If the Y is hydrogen, we will get an aldehyde. If it is an R group, we will have ketones. If it is a hydroxyl group, we can call them as a carboxylic acid. Again, if it is a chlorine, we will call them as an acyl chloride or acid chloride. Further, if it is an OR group, we can call them as an ester. And it is a OCOR group, that is an ester group, we can call them as an acid anhydride. And the last, if it is an amine, we can have the amide. Now we can have a look into the reactivity of these carbonyl compounds. The reactions of alcohols with acid chlorides and with acid anhydrides are the most important ways of making esters. I have taken here an acyl chloride and an acid anhydride. First, we will look into the acyl chloride. Here I am taking an acetyl chloride having the CH3 group here. If I treat this acetyl chloride with an alcohol, that is a cyclohexanol, in presence of a base, so you will get an ester. So this is the ester, we call it as cyclohexyl acetate. Now we can take an acid anhydride. So this is our acid anhydride. I am taking here the acetic anhydride having the CH3 group at both the ends. If I treat this with the same alcohol, that is the cyclohexanol, in presence of the base, you will get the same ester, that is the cyclohexyl acetate. So here, the reaction of these alcohols with these acetyl chlorides give you the esters. So what is the mechanism of this reaction? So we can take the same reaction here, where we are converting an acetyl chloride into an ester using an alcohol in presence of a base. So this is our starting material, that is the acetyl chloride, and the carbonyl group is here. So you know that the carbon here is a partial positive charge and the oxygen has a partial negative charge. And you have the alcohol and the oxygen has the lone pairs. So this can act as a nucleophile. So the acetyl chloride can act as the electrophile. So the lone pairs from the oxygen can attack the carbonyl carbon and this bond can go to the oxygen, and what you will generate is this compound. So once you have this intermediate containing a positive charge on this oxygen here, and you have the base, here we are taking the base, that is the pyridine, and the lone pairs on the nitrogen will attack this hydrogen, and this bond will go to the oxygen and neutralizes this charge. So what you will end up is an unstable tetrahedral intermediate. Since this carbon has 4 bonds and that is sp3 hybridized, we can call them as an unstable tetrahedral intermediate. Why it is unstable? Because the chlorine here is a leaving group. So what is a leaving group? The leaving groups are anions such as Cl minus, RO minus and RCO2 minus that can be expelled from the molecules taking their negative charge with them. So what will happen? This O minus can come down. Since the chlorine is a leaving group, this chlorine can leave a Cl minus, and what you will generate is your final ester, that is the cyclohexyl acetate. Now we can have a look into the acetic anhydride, and we are treating that with the alcohol to generate the same ester, that is the cyclohexyl acetate. So I am taking here the acetic anhydride and the carbonyl group. This carbon is partial positive charge and this oxygen has a partial negative charge, so they can access the electrophiles. And you have the alcohol here with the oxygen containing the lone pairs, so this will be your nucleophile. So the lone pairs on the oxygen can attack this carbonyl carbon and this bond can cleave and go to the oxygen. So what you will generate is this intermediate containing the oxygen with this positive charge here, And we have the base, that is our pyridine, and the lone pairs on the nitrogen will take this hydrogen and which will neutralize the charge on the oxygen. So what you will generate is again an unstable tetrahedral intermediate. So why this is again unstable? This is because we have here the O C double bond of CH3 group. So this is an RCO2 minus group, which is a leaving group. So what will happen? This O minus will come down and this bond will cleave and you will generate the RCO2 minus. Finally, you will generate your final product, that is the ester, that is a cyclohexyl acetate. Why are these tetrahedral intermediates unstable? So I am taking here an aldehyde, and if I treat this with a Grignard reagent, that is the ethyl magnesium bromide. So you are aware here the carbonyl group, the carbon is partial positive charge and the oxygen has a partial negative charge. In the Grignard reagent, we have the metal, that is the magnesium, so it has a partial positive charge, and here the ethyl has a partial negative charge. As a result, this bond is polarized, and this bond can attack the carbonyl carbon here, and this can go to the oxygen. So what you will generate is a stable tetrahedral intermediate. Since this carbon has 4 bonds, that is sp3 hybridized, we can call them as a tetrahedral intermediate. But why in this case it's stable? So if you see the groups that is attached here, we have the CH3 group and we have the ethyl group. So these two groups, that is the CH3 minus and the ethyl, are very bad leaving group. So if you have a proton in your system, the O minus can take this hydrogen and it will form this alcohol. If you see the carbon attached here, which is attached to 2 other carbons, so we can call them a secondary alcohol. Now let's take the acetyl chloride, and we have the alcohol, and we treat this with a base. So what you will generate is an ethoxide. So this is ethanol, and if you remove the proton from here, we will generate the anion that we can call it as an ethoxide. So you have the oxygen here with a partial negative charge and the carbon here the partial positive charge. So what will happen? This ethoxide can attack the carbonyl carbon and this bond can go to the oxygen. We can also draw the mechanism by taking the arrow from the lone pairs on the oxygen that can attack the carbonyl carbon and this bond can go to the oxygen. So what you will generate is an unstable tetrahedral intermediate. So why in this case it is a stable tetrahedral intermediate? If you see the groups here, we have the CH3 minus and the ethyl, they are very bad leaving group. But if you see, it is an unstable tetrahedral intermediate because the groups attached here, the CH3, we have the ethoxide and we have the Cl minus, right? So you know the CH3 is a very bad leaving group, but the ethoxide is not so bad leaving group and the chlorine is the best leaving group. So out of these 3, the chlorine is a best leaving group. So what will happen? This O minus will come down and it pushes the chlorine as Cl minus. So what you will generate is an ester. Now we are going to learn the relation between the leaving group ability and the pK value of the conjugate acid. So the pK is a useful guide to understand the leaving group ability. If you consider an acid HX, so if it has a lower pK value, then the corresponding anion X minus will be a better leaving group in carbonyl substitution reactions. So we can take our previous example where we are treating an acetyl chloride in presence of ethanol and a base. So we are generating this tetrahedral intermediate here with 3 different kind of groups. So if you consider each of these groups and if you try to make it protonated, you get the corresponding acid. So you will get hydrochloric acid, ethanol and methane. If you go down, the acidity of these groups will decrease. That means hydrochloric acid is the most acidic, which has the lower pKa, and methane, which is the least acidic, which has the highest pKa. So if you try to correlate the pKa value with the leaving group ability, then the corresponding anion, the Cl minus, will be a better leaving group and your CH3 minus will be a bad leaving group. For a better understanding, I have shown here a table containing various derivatives of carboxylic acid. So you can see here, this is your carboxylic acid and we have the acyl chloride, or we will call it as acid chloride, and we have our ester, acid anhydride, and amide. So if you see this table here, so we have these the carboxylic acid derivatives and the corresponding leaving groups, right? For example, if you take an acyl chloride, so this is the acyl chloride, the leaving group will be the chlorine. If you take an anhydride here, right, the leaving group will be the RCO2 minus. The black one is the leaving group. And if you take an amide, the NH2 minus, that is the NH2 minus here will be the leaving group. And if you protonate them, you will get the corresponding conjugate acid here. And if you see the pK value of this acid, the hydrochloric acid is the most strong among them, right? And if you consider the leaving group, the chlorine is the best leaving group, and then comes the anhydride, right? The RCO minus leaving group will be the second one, and then it comes the RO minus, that is a poor leaving group. Then we have the NH2 minus, which is very poor leaving group, and you can see finally the alkyl anion, the R minus, that is not a leaving group. So these are the order for the leaving group. You have to keep it in mind. So for example, we can take one reaction. We have taken here an acyl chloride and we are treating this with sodium formate. So this is our sodium formate. So if you draw the structure, it is right HCO2Na. It is like this, right? So this minus charge can attack this carbonyl carbon and this bond can go to the oxygen. So this will be the tetrahedral intermediate that you are generating. So from here, you have to understand which will be the better leaving group. So now you know the CH3, right? So this is CH3 is the R minus. That is not a leaving group. So you don't need to consider that one. But you have to consider these two. So if you consider the Cl minus, it will come in the top part, which is the excellent leaving group. And now you have the HCO2 minus. So if you consider the H as R, then this will come in this category, right? And the last one is the CH3, which will be the most weak leaving group, right? It is not a leaving group. So we can say that the Cl minus is the excellent leaving group among all of the three. So what will happen? This O minus will come down and the chlorine will leave. And what you will get is a mixed anhydride. So this product is known as a mixed anhydride. Now you have learned that the acyl chlorides react with alcohols to make esters, right? Even the acid anhydrides can react with alcohols and give you the esters. So now what will happen if you treat the acyl chlorides with amines? So you will get an amide. So you have to keep this in mind that the acyl chloride or the acid anhydride reacts with alcohols, you will get the esters, and the acyl chloride react with amines, you will get the amides. Now let us take an example. So I am taking here an acyl chloride. So this is an acyl chloride, and if you see this substituent here, so this is an isopropyl group because this one is 3 carbon, right? 1, 2, 3. 3 carbon, and if it is a Y shape, we call it as an isopropyl group. And if you react this with an amine, so here I am taking ammonia, right? So you know that here the carbon has a partial positive charge, the oxygen has a partial negative charge, and your nitrogen has the lone pairs, right? So this can act as a nucleophile. So your electrophile will be the acyl chloride. So the lone pairs on the nitrogen can attack this carbonyl carbon and this bond can go to the oxygen. So what you will generate is an intermediate like this, right? And in this case, we are not using a base. Instead, we are using two equivalent of amines, right? So in the previous case, we are using, for example, a pyridine to take this proton and neutralizes the charge, right? So in this case, we are using one more equivalent of the amine. So once we are using another equivalent of the amine, what will happen? This lone pairs on the nitrogen can take this hydrogen and it will neutralizes the charge on this nitrogen. So what you will generate is a tetrahedral intermediate, right? So you will say now, is this a stable or unstable intermediate? Of course, this is an unstable tetrahedral intermediate, right? Because it contains a leaving group. And if you see, you have the chlorine and you have the NH2 here. So which will be a better leaving group? Now you know the chlorine is a better leaving group. So the O minus will come down and the chlorine will leave, right? So what you will generate is an amide. So this is how an acyl chloride which can react with an amine, you will get an amide. But you have to remember you need to use at least two equivalent of amine for this reaction. So now you see here in this step, Actually, you are generating a side product, that is the NH4 plus here, right? Because this is taking a proton and you are generating the NH4 plus. And in this step, you are generating the Cl minus as the leaving group, right? So this is a positive charged species. This is a negative charged species. So they can combine to that form an ammonium chloride salt as the byproduct. So this will be your byproduct. So now you can try by yourself this reaction that we have an acyl chloride and we are treating this with a secondary amine, right? So you are generating this amide. So now you can try the mechanism by yourself. Now we will learn a similar reaction for the synthesis of amide, that is a name reaction Shorten-Bowman synthesis of amide. So if you take the previous reaction, we are using two equivalent of amine. One equivalent is the first step which acts as a nucleophile. In the second step, this amine will take a proton from this intermediate, right? And you are generating the corresponding amide. Suppose you are not using two equivalent of amine. So what will happen if we are only using one equivalent of amine? So we will generate the first intermediate like this, right? The same intermediate we have here, right? And this can come down. And now we will leave this chlorine from here because we don't have anything to abstract this hydrogen from here, right? So once this happen, what you will generate is this intermediate here. Now you have the Cl minus in your system, right? So this can now take this proton and you will generate the corresponding amide. So what you are generating is a hydrochloric acid. So we are using another equivalent of amine to neutralize the generation of this hydrochloric acid. So if we try the same reaction by using a base, for example, I am using a sodium hydroxide, which is a source of OH minus and which can act as a base, right? So if you replace the second equivalent of amine with a base, so what you will expect is that OH minus can take this hydrogen and you can generate the amide, right? But there is a problem for this reaction. This is because OH minus is also a nucleophile. So if you treat the ammonia along with the base, what will happen? The generated OH minus from this NaOH will attack this carbonyl carbon of this acyl chloride and it will generate a carboxylic acid. So you will get a carboxylic acid. So how can you prepare an amide by mixing ammonia and sodium hydroxide or any other base? So this is what is about the Shorten-Bowman synthesis of amide. So what we want to get, we are taking this acyl chloride and you are treating this with one equivalent of amine in presence of a base. You want to get this amide, right? And you don't want this carboxylic acid. So how the Shorten-Bowman prepare this amide? So what he did, he used a two-phase system containing water and DCM. So you know that the water and the DCM, they are immiscible, right? Because they will not mix each other. And the dichloromethane, which has a higher density, will come down, and the water, which has a lower density, will stay in the upside. So if you see the beaker, so this is the Shorten-Bowman synthesis setup for the amide. So you have the DCM here, whose density is high, so it is staying in the green color in the down part. And you have the water layer, that is the aqueous layer in the top part. So in the lower layer, you can see the dichloromethane is an organic solvent. So the organic compounds like the acyl chloride and the amine will dissolve and create here, right, as a solution. And you have the sodium hydroxide that will stay in the upper side. So in the down part, what is happening? This acyl chloride and the amine can only react and there is no interaction with the sodium hydroxide. So you will achieve the first step without any nucleophilic addition of this OH minus to the acetyl group, right? Then once you have the hydrochloric acid that is generated in the system, right? So the hydrochloric acid is miscible with water. So once you generate the hydrochloric acid, the acyl chloride reacts only with the amine, but the hydrochloric acid produced can dissolve in and can be neutralized by the aqueous solution of the sodium hydroxide. So this is how the Shorten-Bowman prepared the amide. So what he did, he used a two-phase system containing a water and dichloromethane. And the first step for the nucleophilic addition, so that is happened in the lower phase, that is the dichloromethane layer, right? Then once you generate the hydrochloric acid, it dissolves into the upper layer and it reacts with the sodium hydroxide and neutralizes the hydrochloric acid.